Hello, welcome to the course Electronic System Design. Last few lectures we are discussing about implementing a logic level, and using these logic gates we are implementing a digital function using some Boolean algebra expressions. Then we saw that if we use multiple technologies on a single PCB or a single system, these technologies are not compatible to each other and there may be differences in their certain parameters, for example the output levels, and we define the VIH, VIL and VOH, VOL levels so that we can comfortably connect these two types of technologies together without any problem. So, now let us see one of the technologies which is TTL. This is also very widely used in implementing these logic gates along with CMOS logic gates. This TTL family is nothing but transistor logic, where we use transistors like BJTs, to implement these logic functions NAND gate, NOR gate. So, just quickly for today's lecture we will define how the TTL gates actually look like, how they work, and how do we connect them together with TTL or together with the CMOS logic, which is very widely used nowadays in implementing these digital circuits. So, let us discuss how a TTL or the transistor logic look like and how does that work. So, TTL, this is nothing but transistor logic. It uses bipolar transistors and diodes. So, let us see how a AND gate actually look like, which is very simple to implement using diodes. So, we have a resistor and then we connect two diodes . This is input A and this is input B, and we have this terminal as the output. This is a resistance R. Let us write the truth table for this gate. So, this is input A, this is input B, and here we have output. When we apply, let us say, both input as 0 0, 0 1, 1 0 and 1 1. So, let us talk about the very first line, which is 0 0. When we apply A as 0 and B as 0, the output node, which is already being pulled to VDD, which is a high voltage here. So, this node out is high and A node is low. This diode will turn on, and this diode, because it has a very low on resistance, this output node will be immediately pulled to 0 volt, which is at the node A. Node A and node B both are 0. So, the output will be pulled down to 0. So, the output value will be 0 in this case, and for any other line, for example, if A is 0, then this diode will turn on, B is 0, then this diode will turn on. When A and B both are 0, then both of them will turn on. So the output will be pulled down to 0 in all the three cases. In fourth case, however, if both A and B are high, high value is typically VDD. So if this node A and B is high, output node is also pulled down to high through this resistance R. This diode will turn off, both of them. So the output will be kept at the VDD value, which is logic high. So the output will be logic 1. So this is the truth table, which is the truth table of nothing but the AND gate, which we can implement using diode logic. Now if we want to talk about a NAND gate, which is more general gate for digital implementation, the NAND gate, we need to put a inverter after this out so that we can make a NAND gate. This is signal A, this is B, this is VDD, this is R1, this is R2, this is R3, and this is signal out. The truth table of this gate is something like this. We have A and B, and here is the output. So when either of the input is 0, when A is 0 or B is 0, one of the diode or both of the diode will turn on and pull this node X to ground or very close to ground, depending upon ratio R1 and the on resistance of these diodes. So this node typically will be pulled down to a very low value near to 0. When this node X is pulled down to 0, then the base to emitter voltage for this BJT will be very less, and this BJT will be turned off. When this BJT is turned off, the output node is pulled to VDD through this R3. So for any of these three lines where A and B, any of them is 0, the output will be pulled down to high, which is 1, 1 and 1. For the fourth case, when both of the inputs A and B are high, this node X is already pulled to VDD through R1. So these diodes are not there, they are turned off. So this node X is VDD, high voltage. When this node X is VDD, the base to emitter voltage of this BJT is high, emitter voltage is 0 and the base voltage is VDD. So this BJT will turn on and the output will be pulled down to very close to 0, and as we discussed last time, the output node will be nothing but the voltage divider of this R1 and R3. So, the output node will be R1 divided by R1 plus R3 times VDD, and this is typically a very low value, very close to 0. So, output will be, you can assume 0, logic 0 for A is 1 and B is 1. So, this is the truth table of a NAND gate. This is the NAND gate which you can implement using TTL. However, this is not the practical NAND gate which we implement in our digital ICs. There are so many issues with this circuit that we will see in the next slide. The first issue is actually we have to have certain amount of protections at the input stage A and B. If the input is, let us say, overshooting or undershooting, that time we should have certain protection which can protect these diodes from that high voltage stress, and intermediate nodes where the junctions will be immediately turn on or turn off, we need to protect the intermediate circuitries from the reverse currents which is possible in this kind of circuits. So, let us see them, what is the practical implementation of this NAND gate using transistor logic. TTL, the practical implementation or practical realization. So, a practical circuit looks like this. For example, we have this VDD rail, which is, let us say, 5 volt. Now we have the resistance R1, and then we have these diodes for input. This is input A, this is input B. So, when we have these input lines, these are generally a long line which is traveling from the other IC or the other system, and this is typically a copper line which is very large in length compared to these elements. So, there can be certain overshoot undershoot based on the environmental noise or some coupling. We need to protect our input terminals from that high voltage stress. So, for example, we have, this is the ground plane we have. So, we need to connect certain Zener diodes for the protection at the input. So, this is the Zener diode. Similarly, for the pin A, we can also call them clamp diodes. then this side we have an intermediate stage and this is the output node. So this is the typical implementation of a NAND gate using transistor logic. We can see there are so many resistances which are used and so many BJTs we are using in the circuit to have it more reliable compared to the previous stage. Here we have used many diodes which are clamp diodes we are using. These are to protect the inner devices from the high voltage or high current surges which can come from the environment or which can be present locally also within the circuit itself. For example, at midpoint also we are using certain clamp diodes, because when there is a device which is on, this is carrying certain amount of current. As soon as we turn on this device, instantly this the wirings or the devices itself, they have certain amount of parasitic inductance. This current tends to flow despite we are turning on the device. So this current, if we immediately turn on the device, it produces a very high voltage if we are immediately turning on because of this parasitic inductance. So to prevent the devices from this overshoot of voltage, we generally provide a short circuit path through these clamp diodes, so that the inner devices are more reliable if we are switching them at the very fast rate. So we use many protection device within the circuit itself to protect the inner devices from these high voltage or high current stresses. In this we have typically three stages. One is the input stage where we have these two diodes connected to A and B. This is the input stage. Mid stage we sometimes call it phase splitter, which is splitting the phase of these input signal to provide at the two diodes, two transistors at the final stage, and the final stage which has two BJTs. So, this is this BJT structure which is one on top of each other, sometimes it is called the totem pole output or the totem pole pair. Which is very widely used in practical realization of these gates. So, let us compare this TTL and CMOS technology based on their electrical specifications. So, TTL versus CMOS. So, let us say we have TTL this side and CMOS this side. And we characterize them based on multiple parameters. For example, the noise margin. So, from a noise margin point of view, TTL has typically 0.3 on the higher side and 0.4, 0.5 typically on the low side. In CMOS, it is typically fixed as the percentage of VCC, which is 0.3 times VCC. Next, we have input source current. In TTL, it is relatively high in both the cases. Both case means 0 and 1 case. So, this is high in both cases. However, for a CMOS, this is typically very less, even less than 1 microamp in both the cases. Now, very important parameter which is power consumption. So, TTL has relatively high power consumption. However, in CMOS actually it depends on multiple factors, for example the VCC, but typically very low. For the same other parameters, for example for the same frequency, same speed, so CMOS consumes very low power. Output drive current, how much output drive capability the gate has. So the output drive current for TTL is actually asymmetric for high it is 0.4 to 2 milliamp, and for a low state this is 8 to 20 milliamp. So this is very asymmetric. However, for a CMOS it is symmetric. Typically 4 milliamp. Power supply for a TTL logic, the power supply is typically 5 volt or plus minus 10% of it. There is always a variation in the power supply, so we have 5 volt and some variation which is 10%, which is acceptable. So the range for a 5 volt power supply is between 4.5 and 5.5 volt, which is 10%. For CMOS logic, this voltage range is very wide. For older technologies even, this voltage range is typically 3 volt to 18 volt, and this is very specifically we are talking about. However, in recent technologies this voltage supply voltage range is typically 0.9 or 1 volt. And the last point is interconnection. Can we connect TTL to CMOS and CMOS to TTL? So in this, the TTL gate cannot drive CMOS. However, CMOS it can drive TTL. So CMOS can directly drive TTL. So these are the few points which are very different than TTL and CMOS. In TTL the noise margins are 0.3 and 0.5. However, for CMOS it is very fixed value, typically 0.3 or 30% of the full supply range. Input source current is high in both the case for TTL. However, for a CMOS it is very low. That comes because the CMOS, the signal is generally applied to the gate of the MOSFET, and the gate is a capacitor which is a gate oxide is there in the at the gate, which does not draw a static current. So the input current of this CMOS gate is very less. However, in TTL we have seen we have put two diodes. When we put signal as A as 0, this diode turns on and there is a sharp current which is flowing from the supply to this input A, which is grounded. So this current is high, and typically we use to large resistance to limit this current. However, still this current is significant, which is high in both the cases for low as well as high input. Then we come to power consumption. So the power consumption of TTL gates are high relative to the CMOS gates, because for every operation we are flowing certain current either from the input or to the output. So, this has a relatively high power dissipation compared to CMOS, where CMOS draws current during the transition only. There is no static current flowing in the CMOS gates, because the pull up network is dual of pull down network, as we have seen earlier. So, there is very less static current or almost negligible. We have dynamic current in the CMOS logic, but still the overall power is comparatively lesser than the TTL logic. The output drive current is again asymmetric for TTL. For high it can drive up to 2 milliamp, however for a low it can drive up to 20 milliamp. So, this current levels are very skewed. In CMOS typically these are same numbers. We can design PMOS and NMOS such a way that they provide almost the same amount of current for pull up as well as pull down. Power supply for a TTL gate is typically 5 volt plus 5 volt plus minus 10%. So, range is 4.5 to 5.5. For a CMOS it is wide range of voltages. For older technologies we used 5 volt, 3.3 volt, 1.8 volt and so on. In modern day technologies we are very shrinking down the voltage to save the power, and typically we are like 0.9 volt and 1 volt supply range. So, this is the supply range for a CMOS logic gates. Interconnection, which is very important, because if we are using a TTL logic and we are using a CMOS logic, at some point of time we have to connect them together to implement a logic function. That time a CMOS can drive a TTL gate. So, for example, we have a gate A which is CMOS and gate B which is TTL. So, this output of A can be connected to the input of B which is TTL gate, and this CMOS gate can drive this gate B which is TTL. However, the reverse is not true. If we take this logic gate B, the output of B is connected to the input of A which is CMOS gate, that time this TTL gate cannot drive a CMOS gate, because there is a difference in the VIH VIL level for a TTL gate compared to the CMOS gate. CMOS is very symmetrical, however, for the TTL gate the VIH VIL level and VOH VIL levels, these are not very symmetrical. Let us see how that happens and what we can do to prevent this problem or to rectify this problem, so that TTL can drive the CMOS gate as well. There are techniques to implement which can rectify this problem. However, in the direct case TTL cannot drive the CMOS gate. Let us see what is the difference in VIH VIL levels and VOH VOL levels. So, let us discuss CMOS TTL interfacing. So, let us first consider when a CMOS is driving a TTL gate and there is no problem. So, we have a CMOS gate which is driving a TTL gate. So, in this case, let us draw the input voltage range and output voltage range for both of these gates. So, for a CMOS, this is the complete voltage range from 0 to VDD. and this is the voltage range for TTL gate at the input. So for a CMOS, typically the VOL level is very close to the ground. This is the VOL level. For a CMOS, and VOH level is very close to the supply voltage. This is VOH for a CMOS. So the output becomes immediately lesser than VOL in case of low, and output will be immediately above than VOH for a logic 1. However, TTL, which is a skewed circuit, so this is typically 0 volt, this is VDD. The low voltage is typically, let us say here, this is the VIL level for a TTL, and VIH, because these are skewed, it is not same as VIL, or this percentage is not same as this. So VIH level is, let us say for example, up to this point. For a TTL, let us say VIH is at this point. So VOL, VOH for a CMOS is symmetrical. However, for a VIL, VIH for a TTL, these are not symmetrical. This is, let us say, smaller, and this is the larger one. Still, the CMOS can drive TTL because when the output will be higher than this voltage VOH, this is definitely detected by the TTL because the VIH level is lower than this VOH. So when the signal will become VOH, that is still within the range of this VIH and VDD. So this signal will be immediately detected by TTL, and this signal which is VOL or below, this is detected by TTL because the signal itself is lesser than VIL and below. So this is overlapping with this signal. So this voltage range VOL is lesser than VIL, so the low will be detected easily, and VOH between VDD and VOH, this is still in between VDD and VIH, so this high also will be detected easily. So CMOS can directly drive TTL. Let us see the other case where TTL is driving the CMOS. So now we have the first gate is TTL and the second gate is CMOS. This is TTL and this is CMOS. Now we know that the TTL, the VIH, these voltage levels, these are skewed in TTL. CMOS, they are symmetrical. So let us draw the voltage levels for TTL. because TTL output is going to input of CMOS. So for TTL we need to write VOL, VOH levels, and for CMOS we need to write VIH, VIL levels. So for a CMOS, this is symmetrical VIH, VIL levels. This is VIL for a CMOS, and this is VIH for a CMOS. Now for TTL, the output voltage is typically, let's say, here VOH level, VO, this is VOL, and VOH is typically like this. This is VOH level. Now we have a problem in case of TTL driving CMOS, because if we see this VOH level is lesser than the VIH level. So what does it mean? When my TTL is driving high, is trying to put a 1 here, this 1 can be this VOH and above any level. So in the worst case, for example, this 1, logic 1 is nothing but VOH itself. So the TTL is driving a 1 at the level of VOH, which is perfectly fine for a TTL. However, this logic 1, this voltage falls at this point for a CMOS, which is not above than VIH, and VIH is the level above which only CMOS will detect it as a 1. So CMOS is going to detect any voltage as 1 only if this is higher than VIH and lower than VDD. So in this range only logic 1 will be detected by CMOS, but TTL is driving a 1 which is only at VOH level, which falls in the undeterministic state or the random state in between this voltage levels VIH and VIL. So this VOH is not directly detected as 1 because there is a voltage difference. This output of this TTL at this point is not high enough to be detected 1 by the CMOS gate. So this is the problem when TTL drives CMOS. So we can write the TTL cannot directly drive CMOS. And why this problem actually comes when we are driving a high, that is actually the output node we are driving high through a resistance and through maybe another BJT, which is driving current to the output, and because of this current and resistance is already there. So there is a definite IR drop in that resistance. Because of this IR drop, the output is not actually pulled completely to VDD, but to a lower value itself. This, because of this lower value, the VOH levels of TTL gates are generally lower. So this is the problem where we cannot put a TTL gate directly driving a CMOS. This VOH level should be higher enough for a TTL gate, and the problem as we see this resistance, and there is a current because TTL drives current, the BJTs are current control devices, so they draw certain amount of current. This current when flowing through this resistance creates certain resistive drop. So, because of this resistive drop, VOH levels are generally lower. We cannot, this resistance cannot pull the output node to high value. So, this is the problem. Now, how can we rectify this problem? We need to find a solution where my previous IC is a TTL gate, a NAND gate which is made up of TTL devices, and the next stage is a CMOS logic, which is for example a microprocessor or maybe some other gate made up of CMOS. How do I connect them together? One solution is, because this resistive drop will always be there no matter what we do, because of this current flowing in the resistance, this IR drop will always be there. So, this resistance itself will not be able to pull this output node to a very high value VOH, because there is a BJT there which is drawing this current to this resistor. So, what we do, we put a external pull up resistance in certain cases. We make a open drain kind of structures. Open drain is the structure where we have only the pull down network, not the pull up network. For pull up network, we externally use a pull up circuit. This pull up circuit is nothing but a single resistance which is used to pull up the output node when none of the pull down network is pulling it down. So, we connect a pull up network which is a typically high resistance. We can easily pull the output node down if we have to, using these pull down network which are very high strength compared to this resistance. And when we need to write 1 here at the output, we switch off the pull down network and the output will be pulled to high value using this pull up network. So, this is how we can rectify this problem. This output node will be pulled to very high value. So, the VOH level of TTL gate increases to a high value and it can drive the CMOS logic gate satisfactorily. Let us see how that is done. So, in the case of TTL driving a CMOS, this is VDD and this is ground. We connect a pull up resistance. So, this is resistance R pull up. This pull up resistance is put such a way that when this output node, or let us say the intermediate node between TTL and CMOS, I and T, when this intermediate node should be pulled down, the pull down network of TTL is strong enough so that this input node is bring down to 0. When high need to be written here at the input node, pull down network is turned off and this intermediate node is charged to VDD through this R pull up. So, this R pull up is called the pull up resistance Now we have some constraints on putting this pull up resistance. If R pull up is very low, means less than 10 kilo ohm, let's say, then pull down network PDN of TTL increases. The pull down network of TTL should be strong enough so that this int node can be pulled down, because the R pull up is very low, less than 10k. If we keep R pull up as very high, let's say very less than 10k, typically giga ohm or so, then this R cannot provide enough current to intermediate node, and it cannot pull up the intermediate node immediately. So, the input node rising will have very slow response. It means the speed of operation decreases. So, we have now a trade off between the PDN of TTL versus the speed of operation. If we have pull up resistance very high value, very big resistance we use, then it will not be providing enough current to pull up the node. So, the response will be very sluggish, the rise will be very sluggish, and the speed of operation actually comes down, which is not a very good thing. However, if we put R pull up as very low, typically let us say 100 ohm or 200 ohm, then when we want to put intermediate node 0, we will turn on the pull down network. That time resistance is very low, it is providing so much of current that pull down network need to provide so high current to pull the input node down. So, there is a fight between the PDN network and the resistive network to put the intermediate node to high value. Pull down network should be strong enough to pull this intermediate node to ground. So, the size of this PDN network increases, which is not again not a good thing, because if the size increases, the overall cost of the circuit increases and the power dissipation of the circuit also increases, because there is so much of current flowing between supply rails VDD and ground through R pull up and the PDN network. So, we have these two kind of drawbacks. We need to align in such a way the value of R pull up so that we meet both of the goals. So, this R pull up need to be designed very carefully so that we have decent speed along with the decent power consumption. So, this is how you can connect a TTL to a CMOS logic using pull up resistance. So, this is all for today. Thank you.